So what I want to do in this video is find the electric field due to a finite line of charge. And so over here what I have is a line charge that lies on the x-axis. And what I want to find is the electric field at an arbitrary position P that lies on the y-axis. And so notice that the electric field at P has both a y component and an x component. And what I want to do here is just find the y component. And so we just want to find the y component for now. And so the total length of the line charge is L, and the line charge begins at the on the x-axis at the coordinate x1 and it ends at the x-coordinate x2. And x1 corresponds to the angle theta 1, which is this angle right here, the angle from the y-axis to the angle corresponding to x1, and the angle corresponding to x2 is theta 2 right here. And the letter R shows the shortest distance from the point P to the line charge. And so note here that the line charge has a total charge of Q, and we're going to denote the line charge density as the total charge Q divided by the total length of the line charge. And so note here that we have a really small segment of the line charge, and that's called dx. And dx just means a really small element of the line charge. And this really small element dx has a charge dq, and we want to find the electric and this charge dq, it produces an electric field dE at point P. And what we want to do is we want to find the y component of the electric field produced by this really small element of charge dq. And so if we were to write the really small this really small amount of charge dq is going to produce a small electric field denoted with dE. And so we want to find the electric field at point P. And in order to do that, we would have to come up with an expression for the electric field due to this segment of charge. And so what I drew over here is the segment of charge and the arbitrary point on the y-axis that we're interested in. And we want to find the electric field due to this line of charge at this point P. And so the equation that gives us the electric field at this point is just given by the electric field is equal to the electric force between two charges divided by the charge Q. Now, what is this charge Q? This charge Q is just an arbitrary charge that we place at this point P, or we place this charge Q at the point that we're interested in at for finding the electric field. And so we want to find the electric field at this point. So we just arbitrarily call this point, we arbitrarily place a point charge of Q at this point right here, point P. And so the electric force occurs when there's two charges involved. One of the charges is Q, but the other charge, let's consider a very small segment of this line segment, and that has a width, that has a length of dx. And dx is also shown on this diagram right here. And let's say that this segment dx has a really small amount of charge dq. Now the letter d just signifies that the amount of charge is infinitesimally small or really, really small. And the letters dx just represents a very small segment of the line charge. And so we have our two charges. One is charge Q, which is at point P, or the point of interest, and the other is charge dq that lies on the line segment. And so this line segment, or this really small amount of charge, is going to produce a really small amount of electric field at point P. And we can denote that with this vector right here. So this really small amount of charge, dq, it's going to produce a very small amount of electric field. We'll denote that with dE at point P. And dE just means a really small amount of electric field. So similarly to this equation, we could also write that dE, or a very small amount of electric field at this point, is equal to the electric force between this charge and this charge divided by the arbitrary charge Q. And so we can expand this out further. We know that the electric force between two charges is just given by Coulomb's constant, which is K, times one of the charges. Let's say one of those charges is Q, times dq, which is the very small amount of charge on the line segment, and that's divided by r squared. And r is just the length from point P on this diagram all the way to the the really small segment of charge that we're considering. So r is just the shortest length from point P to dx, or it's this line right here. And so if we divide f the electric force between the two charges by Q, what we get is that Coulomb's constant times the charge at point P times dq divided by Q times r squared gives us that Q, we can simplify this further because Q divided by Q is, well, those will cancel out. And what we're left with is actually that K, Coulomb's constant, times dq divided by r squared. That will equal the really small amount of electric field at point P, which is this point right here. So the really small amount of electric field at a point on the y-axis is just given by Coulomb's constant times a really small amount of charge on the line segment right here divided by r squared. That's equal to dE. And so this is the expression that we're going to use to find the x component of the electric field at point P. And just to note, this really small amount of electric field is only produced by this single segment. It's only produced by this single really small amount of segment on the line charge. In order to find the electric field produced by the entire line charge, we would actually have to break up this segment into really small pieces, and each of those pieces will have a charge of dq. And so if we were to write the amount of electric field produced by this really small charge dq, we would write that the element of the electric field is equal to Coulomb's constant times the really small amount of charge and divided by r squared. And remember that r squared is just the distance from point P to the distance from point P all the way to this really small segment of the line charge dx. And so what this is saying is the magnitude of the field produced by this small amount of charge dq is given by this expression right here. But remember, we want to find the y component of the electric field at point P. But what we have right here is just a really small amount of electric field caused by this small amount of charge. But we want to find the y component of the electric field produced by this charge. So if we want the y component, and so notice here that the electric field at point P has two components, the y component and the x component. But we just want the y component, which points upward in this direction. And so if we want the y component of the electric field, we would have to multiply this by some trigonometric function to get this the electric field in the y direction, or the y component of the electric field. So if we were to draw a triangle, we could find which trigonometric function to use to find the y component. And so if I redraw this triangle right here, this arrow right here, this vector right here represents the electric field at point P, or a really small amount of electric field at point P caused by this really small amount of this really small segment of the line charge. And so this arrow right here that's pointing vertically upwards is just the y component of the electric field. And the one that's pointing horizontally is just the x component. And the angle between them is just theta. And this angle right here is just the same angle right here that's pointing opposite to this angle. And so if we recall back, we know that the cosine of theta is equal to the adjacent side over the hypotenuse. And the adjacent side is just, and the adjacent side to this angle theta right here is just the y component of the electric field, which we can denote with dEy, and the hypotenuse is just dE. And so what this means is that we're solving for, we want the electric field in the y direction. So if we solve for dEy in the y direction, we get that dE times the cosine of theta would give us the electric field at point P in the y direction. And so this right here is just dE, and all we have to do is just multiply this by the cosine of theta, because this right here is the electric field in the y direction, and this right here is the magnitude of the electric field, and this right here is just the cosine of theta, which when we multiply the cosine of theta with the magnitude of the electric field at point P, we get the electric field in the y direction. So this means that the electric field in the y position is given by k dq divided by r squared times cosine of theta. And so let's say that the vertical distance from the origin all the way to point P is y, or we can denote this vertical distance with the letter y. And the angle theta, or the cosine of theta, corresponds to this angle in this triangle right here, this angle right here. And so if we redraw that triangle, what we see is that the angle goes right there, and this side of the triangle is just given by the vertical distance y, and this opposite side to the angle is just x. And so the cosine of theta in this case, remember that the cosine of theta is just the adjacent side over the hypotenuse side. And the adjacent side to the angle is just y, and the hypotenuse is just the distance from point P all the way to this small segment of the line charge dx, and that's given by the letter r. And r is just used to denote the distance from point P all the way to dx. So the hypotenuse is just r. And so we can substitute this cosine of theta, we can substitute this into this expression right here. And so if we multiply this, r times r squared is just r cubed. And so the next thing that we need to define in this equation here is the variable r. And so note that the variable r is just the distance from point P all the way to this small element dx. So we just need to find, or we just need to come up with an alternative expression for r in terms of x and y. So if we draw out this triangle right here, we get that this side right here is the letter y, and this length right here is x. And the angle is theta, and the hypotenuse is r. So if we use Pythagorean's theorem, we know that this side, since this is a right triangle, we can just say that x squared plus y squared equals r squared. And if we take the square root of both sides, we get that r is equal to the square root of x squared plus y squared. But we want r cubed. So one way to rewrite this expression right here is just to say that x squared plus y squared is raised to the 1/2 power, because raising this to the 1/2 power is the same as square rooting this entire expression, and that's equal to r. But we want to cube that. So if we cube that, or raise it to the 3rd power, we would just have to raise this entire side to the 3rd power, and that would just multiply everything inside of here. That would just multiply this exponent right here, the 1/2, by 3. And so 3 times 1/2 is just 3/2. So what we could instead write is just x squared plus y squared raised to the 3/2 is equal to r cubed. And so we can substitute that into r cubed in this expression right here. So the next expression, or the next variable in this expression here to change into in terms of x and y is dq. And because we already defined r cubed as x squared plus y squared raised to the 3/2, and K is just Coulomb's constant, which is a constant. And so over here, we're given that lambda is just the line charge density, or the density per unit length of this finite line charge right here. So we could just write that as the total charge divided by the total length of the line charge. So over here, we're given a relationship that says dq is equal to lambda times dx, which is basically saying that a small amount of charge is just equal to the line charge density times dx. And remember that dx is just this very small distance, or this very small segment of the line charge, and that's denoted with dx. So if we want the small amount of charge given by this small segment, it would just be the line charge density lambda times the length of the segment dx. So we could just substitute in dq, we could just substitute in lambda times dx into dq. And so now this is the final expression, and we just went from the initial expression into this one, and this final expression right here is in terms of x, y, and other constants like k and lambda. And so now the electric field at point P, or the y component of the electric field at point P, is given by this expression right here. But remember, this expression right here only corresponds to the small electric field produced by this small segment of charge dx. But we want the electric field at point P due to the entire charge, not just the small segment of charge dx. And in order to use that, we would have to integrate both sides. And if we integrate both sides, we would get the electric field at point P in the y direction for the entire line charge. And so this expression right here only gives us the electric field in the y direction due to the small segment of charge on the line charge. But we want the electric field due in the y direction due to the entire charge from x1 all the way to x2. And in order to solve that, we would actually need to integrate both sides. And the reason we integrate both sides is because each of this entire line charge right here can be broken up into little segments of charge. And we could sum up those charges, and each of these charges has a length dx. And we could sum up all of those really, really small charges, and we could find the individual electric field component due to these small charges at point P. And then we could add all of those up, and then that would give us the electric field at point P, which when we do that, that's the same as integrating both sides from x1 all the way to x2. And so since we're integrating this from x equals x1 to x equals x2, the lower limit on this integral is just x is equal to x1, and the upper bound, or the upper limit, is just x equals x2. And so again, integrating both sides is necessary because we're finding the individual contribution of this line charge, or we're cutting up this entire line charge into smaller pieces, and we're finding the individual contributions due to these really small pieces of charge at point P. And when we do that, we're pretty much just integrating both sides. And so remember, when we take the integral, we can actually take out constants from our integral expression, and then we just keep in the variables that are changing. So in this case, K, the Coulomb's constant, is a constant, and we can take that out of the integral. And lambda, which is the linear charge density, is also a constant, so we can take that out of the integral. And so we can just rewrite that as k times lambda, and then the integral from x equals x1. And remember, x1 is the point at which the line segment starts, and all the way to x equals x2. And x2 is the point at which the line segment stops, or the final coordinate of the line charge. And the only thing remaining in this integral is just dx divided by x squared plus y squared raised to the 3/2 power. And so x squared, and also note here that we're taking this integral with respect to x, because the variable that is changing here is x, and x is just the distance from the origin to the point at which the line segment, or the really small line segment, dx is. So x is from the origin all the way to the small. And so since we're cutting up this line charge into really small components, the value of x is actually changing. So we're cutting it up into really small segments, and so the value of x is, for this first really small segment, is x, and then for this other really small segment is also x, and it just keeps, and for each other segment, the variable x keeps changing, and it goes from x1 all the way to x2. And so the variable x is constantly changing from x equals 1 to x equals x1 to x equals x2. And so that is why we integrate from x equals x1 to x equals x2, because the variable x is the variable that is varying, or it is the variable that is changing. But note that the variable y is just the distance, the vertical distance from point P to the origin. And so the variable y is just a constant, but the variable x is constantly changing. And so if you take the integral of dE in the y direction, you're finding the electric field at point P in the y direction due to each of these small segments of charge. And each of these small segments have a width or a length of dx. And so if you take the integral of dE in the y direction, you get the total electric field in the y direction at point P. And if you take the integral of this expression right here, you would get this entire expression right here, 1 over y squared, and then x2 divided by square root of x squared plus y squared. And so if we wanted to simplify this a little bit further, what you would find out is that the sine of theta is equal to the opposite side over the hypotenuse side. And if we wanted the sine of theta 2, angle 2 is this angle right here. And the opposite side to this angle 2 would just be x2. Because in this larger triangle right here, if we were to draw the triangle out, we have that theta 2, and we have the vertical distance y, and theta 2 corresponds to x2, and the opposite side to the angle is just x2, and the hypotenuse is just this side squared plus y squared. And similarly, if we did that for sine of theta 1, we would get that at the opposite side to theta 1 on here, that corresponds to x1 divided by the hypotenuse. And we get the hypotenuse by using Pythagorean's theorem. And so note that we can substitute in these expressions for sine of theta 2 and sine of theta 1 into these expressions inside of the parentheses. And if we substitute it in, because the opposite side and the hypotenuse side match what's inside of the parentheses here. So we can just substitute in sine of theta 2 right here and sine of theta 1 right here. And so simply by substituting in sine of theta 1 into these expressions inside of the parentheses, we simplified the electric field in the y direction at point P to this expression right here. And note that we can also further simplify this since y divided by y squared is just 1 over y. So the electric field in the y direction at point P, at an arbitrary point P, is given by k times the linear charge density times 1 divided by y times the sine of theta 2 minus sine of theta 1. And also note that, and also recall that the linear charge density is just equal to the amount of charge for a given length. So we can substitute in Q, the charge, the total charge divided by the length into the linear charge density right here to get a more simplified expression. And so the simplified expression for the electric field in the y direction is given by this entire expression right here. So we found the electric field in the y direction, but what about the electric field in the x direction? So now we want to find not the y component, but the x component of the electric field at point P. And so over here, I redrew the triangle that corresponds to this triangle right here. And so we know that this side right here, the hypotenuse, is just dE, and the vertical vector is dEy. But now what we want to find is the electric field at point P in the x direction. And the angle right here is theta, and this angle right here corresponds to the angle that starts from the y-axis to the element or the section of the line of charge dx. And so if we recall that the sine of this angle, sine of theta, the opposite side divided by the hypotenuse, and the opposite side to theta is just dEx. But also note that since this vector right here points in the left direction, or points this way, we would have to take the direction into account. And so we're going to take, on our y-axis right here, we're going to take upwards as positive, and to the right as also positive. And since the vector points in the negative direction or the opposite direction, this vector right here would actually be negative since it points in the left direction. And divided by the hypotenuse, which is just dE. And so the simplified expression for the electric field in the y direction is given by this entire expression right here. So we found the electric field in the y direction, but what about the electric field in the x direction? So now we want to find not the y component, but the x component of the electric field at point P. And so over here, I redrew the triangle that corresponds to this triangle right here. And so we know that this side right here, the hypotenuse, is just dE, and the vertical vector is dEy. But now what we want to find is the electric field at point P in the x direction. And the angle right here is theta, and this angle right here corresponds to the angle that starts from the y-axis to the element or the section of the line of charge dx. And so if we recall that the sine of this angle, sine of theta, the opposite side divided by the hypotenuse, and the opposite side to theta is just dEx. But also note that since this vector right here points in the left direction, or points this way, we would have to take the direction into account. And so we're going to take, on our y-axis right here, we're going to take upwards as positive, and to the right as also positive. And since the vector points in the negative direction, or the opposite direction, this vector right here would actually be negative, since it points in the left direction. And divided by the hypotenuse, which is just dE. And so if we solve for the electric field in the x direction, if we multiply both sides by dE, we would just get that dE times the sine of theta, and there's a negative sign over here. So if we multiply both sides by -1, we would get the negative over here. And remember that dE just represents a very small amount of electric field caused by this really small segment of charge. And this small segment has a width of dx and has a charge of dq. And this creates a small amount of electric field at point P. And so if we just substitute in dEx over here, we would just get that -1 times dE, and that's just the magnitude of the electric field, which is just given by Coulomb's constant, times the small amount of charge dq over r squared. And remember, r squared is just this length right here from point P to the segment that we're interested in. And that's multiplied by the sine of theta. and we would just get x divided by r. And remember, this is just equal to a very small amount of electric field that points in the x direction at point P. And it's negative because it points in the left direction. And so if we define R is the hypotenuse in this case, and that's equal to, just using Pythagorean's theorem, we know that this side squared, x squared plus y squared, is equal to r squared. And if we take the square root of both sides, we would get that, just like before, we have the same value of r. And since r squared times r is r cubed, we would have to cube this expression right here. So another way to rewrite this is just r raised to the 1/2. R is equal to x squared plus y squared raised to the 1/2 power. And so cubing this expression would just change 1/2 to 3/2, similarly to over here. And so if we substitute in that dq is equal to lambda times dx, where lambda is just the linear charge density, we would get this expression right here. And so just to recall, linear charge density, lambda, is just the amount of charge over a certain length. And a dq just represents a very small amount of charge that's equal to the linear charge density times dx. And so once again, what we're actually doing to find the electric field in the x direction at point P is we're actually cutting up this entire line segment right here into really small pieces that have a width of dx. And each of those pieces are going to have a small amount of charge dq, and those are going to create a very small amount of electric field in the x direction at point P. And if we add up all of those contributions to the electric field in the x direction at point P due to these small amounts of charge, we would finally get the x component of the electric field at point P. And so that is why we would have to take the integral of both sides with respect to dx. And so since we're integrating it from the starting point, which is x1, and the ending point, which is x2, our bounds of integration are just x equals x1, and the upper bound is x equals x2. And so recall that when we're taking the integral, we can actually take out constants from the integral. And so the constants in this case are just k coulombs, which is Coulomb's constant, and the negative sign, which stands for -1. And the linear charge density is also a constant. And but x right here, x is not a constant, because just like before, when we found the electric field on at point P due to due to this line charge in the y direction, we integrated it with respect to x because the distance from when we cut up this line segment into smaller and smaller pieces, each with the width of dx, the distance from the x-axis changes. So at one moment it's this value of x, but at the other moment it's this value of x, and so the value of x is changing. And it goes from x equals x1 to x equals x2. And so x in this case, it would not be a constant, but y, which is just the vertical distance on the y-axis, is a constant. So we can take out all of these constants from our integral. And so this is the final integral expression, and we took out all of the constants, k and the linear charge density and the negative sign, and we left in the variables that are changing or that are varying. And so you can use any online calculator or any calculator and to find the integral of this expression right here, but just make sure you note that the variable y is a constant. So you treat it like a constant, like any number. And the variable x is the variable that we're taking the integral with respect to, and that's the variable that is changing. And so if we evaluate this integral, the expression that we're going to get is going to be equal to the integral of dEx. And so if we take the integral of this side, dEx, we just get the total electric field at point P in the x direction. And so evaluating this integral gives us this entire expression right here. And you can check this using a calculator online. And so I want to simplify this expression down further. And previously, when we found the electric field in the y direction at point P, we also had a very similar expression, and we used sine of theta to simplify this down further. And let's do the same for this expression. So if we draw out a triangle that goes from point P to the small segment dx, we know that this side right here is just y, and this side right here is just x. And this side is the hypotenuse is r. And the angle right here is just theta. And so r is just equal to the square root of both of the square root of the sum of the squares of both of these sides. And so let's find the cosine of theta. That would just be equal to the adjacent side over the hypotenuse, which is denoted with hyp, and the adjacent side to this angle is just given by y, and the hypotenuse is given by r. And so remember that r is just equal to the square root of the sum of the squares of both sides. So if we substitute that in, we just get that x squared plus y squared. And so the line charge starts at x1, and the angle between the y-axis and x1 is given by theta 1. And the line charge ends at x2, and the angle between the y-axis and the x2 is given by theta 2. And so if we were to write the cosine for theta 1, well, that would just be y, the adjacent side, which is still y, but divided by the square root of x2 x1 squared, since the triangle that we're considering is this triangle right here. And so we're dividing by the hypotenuse, which in that case would just be r, and the x coordinate would just be x1. And so it would just be, we would just square x1, and we would add that to y squared. And similarly for theta 2, the triangle that we have to consider is this triangle right here. The angle between the y-axis and to x2 is theta 2. And so the adjacent side, it would still be y, but the expression for the hypotenuse would change, because now the horizontal distance on the x-axis is now x2. So cosine of theta 2 is equal to y divided by x2 squared plus y. And so note that both of these expressions for cosine of theta 1, which is given by this expression, that's very similar to this expression right here, except that there's a variable y on the top. And for cosine of theta 2, it's given by this expression, and that is very similar to this expression right here. And so that we can match, or that we can have identical expressions, we can just divide both sides by y, and that would give us that would eliminate the y variable on the top, and that would bring the y variable over to this side. And so doing that, we would get that the cosine of theta 1 divided by y is just equal to x1 squared plus y squared. And similarly for cosine of theta 2, we can just divide both sides by y, and we would get that the cosine of theta 2 divided by y is equal to 1 over x2 squared plus y squared. And so we could easily, now we have identical expressions. This expression right here matches this expression, and this expression right here matches this expression. So we could easily substitute in the cosine of theta 1 divided by y into this expression, and we can substitute in cosine of theta 2 divided by y in for this expression. And that would further simplify down this entire expression. And so now our simplified expression is this. We replaced 1 over x1 squared plus y squared with this cosine of theta divided by 1, and we replaced this expression with cosine of theta 2 divided by y. And so note that both of these expressions have the variable y, and so that means that since both of them have common variables, we can factor those out and take those out of the parentheses, since both of these terms have a common variable. And also note that there's a negative sign at the front, and so we can actually distribute this negative sign into the parentheses to further simplify the expression. And when we distribute this negative inside, then that means that this term is going to obtain a negative sign, and when we distribute this negative sign in, then this negative times a negative is a positive. And so our simplified expression for the electric field at point P in the x direction is this entire simplified expression. And we factored out the variable y, and we distributed this negative sign inside, and that's the reason why we switched cosine of theta 2 to this position, and that's why we switched both cosine of theta 1 and cosine of theta 2, because we distributed this negative. And also remember that the linear charge density is the total charge divided by the total length of the line segment. So we can just substitute in this expression into this linear charge density variable, and we can further simplify this expression. And so now we have the electric field in the x direction at point P, and we have the electric field in the y direction at point P. So if I redraw the triangle at point P, it would look something like the hypotenuse is the magnitude of the electric field, and the vector pointing in the vertical direction, that would be the electric field pointing in the y direction, and the vector pointing to the left is the electric field in the x direction. And so note that this is a right triangle, and the 90-degree angle is right there. And so we can just use Pythagorean's theorem and remember that the hypotenuse, which is E, the square of that is equal to the electric field in the x direction squared plus the electric field in the y direction squared. And if we wanted the total electric field at point P due to the line segment, we would just take the square root of both sides. And that would eliminate the square on the electric field. And so we could just plug in the electric field in the x direction right here and the electric field in the y direction right there, and we could get an expression for the total electric field at point P. And so we substituted in the electric field in the x direction, and we squared that because of Pythagorean's theorem, and the electric field in the y direction, we also squared that. And this is the expression we got right here. And all of that is equal to the total electric field squared. So we can distribute this square, this exponent, which is a 2, we can distribute that into here. And we can also distribute this exponent of 2 into here. And each of these terms would be squared. So this entire expression, kq over ly, each of these variables would also be squared. And this entire parentheses, cosine of theta 2 minus cosine of theta 1, that would also be squared. And in sine of theta 2 minus sine of theta 1, that expression would also be squared. And so when we distribute this exponent into kq over ly, we get k squared times q squared divided by L squared times y squared. And then since both of these terms have this expression right here, the kq over ly, since both of these terms have that in common, that means that we can factor out the kq divided by ly after we've distributed the exponent. And if we do that, we get this expression right here. And so we factored out this k squared times q squared divided by L squared times y squared, because both of these terms have this expression here in common. And so our final step would just be to take the square root of both sides, since the electric field here is squared. And so notice that when we take the square root of both sides, we can actually take out this entire expression right here out of the square root, because each of these variables here are squared. So we can just take those out of the square root. And so when we take the square root of both sides, the final expression for the electric field at point P is this entire expression right here. So the value of the electric field at point P, or the total electric field at point P, is this entire expression.